So, I know you've all been waiting for this. This is the first talk, which is on the mathematics of protein structure determination. Loredana, Iacob, is going to talk about Bragg's law and the foundation of solid state chemistry.
Thank you for being here. I'm a little nervous. This is honestly a big project for me, and it might help me a lot with some foundation, everything that means researching. But have you ever wondered how is the structure of the protein determined? Probably not, because you're not into different stuff. But this is actually 90% mathematics. 90% of how we figured out the function of proteins in our body is mathematics. And third, let's find out. First of all, I'm going to introduce you in the context of how we determine the structure. Then I'll provide some background in the physics behind it. I'm going to prove the most important law in this scenario. And finally, we're going to make we're going to determine the structure of a protein. So let's see. Proteins can be arranged in a crystalline structure like this. And an X-ray can be directed at it. It's going to pass in different planes of atoms, and it can interact with the protein or it cannot. And then it's going to interact with the protein with the X-ray, and so on. What happens when it interacts? It will hit the protein, it will be reflected in a certain way, in a certain direction, because it needs to be symmetric, as we're going to figure it out. And everything that is reflected is going to interfere, and it's going to form a diffraction pattern, just like this. This is the raw data. This is what scientists use to determine the structure. But behind this, it's a lot of struggle because people didn't actually know how waves interact. We knew that in water, for example, they will form maximum and minimum, but when we're talking about microstructure, such as protein and X-ray, we don't actually know what happens. We don't know if they get reflected elastically, if they're absorbed and we get out something completely different. So a few theories were proposed by Maxwell Law and Lawrence and Henry Bragg. Interestingly, Maxwell Law proposed that the proteins, the atoms in the crystal absorb the X-ray and it emits something else. But it was proven by the father and team son Lawrence and Henry Bragg that this is not correct. And in fact, later research proved that Maxwell Law's experiment was only correct because he wanted it to be correct. He changed the data in order to won his Nobel Prize. But Lawrence, at the stunning age of 22, being to this day the youngest laureate of a Nobel Prize, proposed the correct theorem, that being that the ray is reflected elastically. He was basically just playing with some crystals and some light in his room, and he figured out this huge theorem. What is stopping us from doing research? And his father then developed the X-ray crystallography, like the machine we actually use today. But when the protein goes into crystal, he said that when the incident ray to the X-ray is reflected on the surface of a crystal, like have you seen in the image with the protein crystal that the proteins are in parallel levels, and each plane can reflect the X-ray, sorry. And the way it is reflected is the same as when you reflect light to a mirror, and it will reflect with an reflection angle the same as the angle theta. That's the angle between the plane and the incident ray. The law behind the mathematics states that the 2 times the distance between the planes times the sinus of this angle theta, it will be equal with the integer multiple of the wavelength of the ray. But let's see how it looks like actually. So these are the planes of the crystal, and this is the ray that is reflected. The ray has a wavelength that looks like this, and when it interacts with an atom here, it will be reflected and it will keep the phase. The phase being how much and how little this ray is actually the height, okay? On the next ray, for example, it will not hit something here, it will pass to the next plane that's parallel to the first one, and we don't know in which phase it will hit the panel. the second plane. So how do we know that this distance here will allow the interference later? When they interfere, in order to an interference to take place, they need to be in the same phase. The height should be at the same place with the height and the lowest to the lowest. So if it goes a certain distance and the phase series is equal like in the picture, for this will look exact opposite. It can look like this, and the maximum here will cancel the minimum here. So basically plus something and then we subtract that and we don't get anything. In this picture, the maximums add to each other to get a new maximum. And when we have a diffraction pattern, these maximums are recorded by the photographic plate. This seems like an easy concept. You get a plane, you get a ray, it's reflected, but not all crystals look like this. Here, it's perfect. Everything is where you just pass by, you know where everything is everything. But real crystals look like this, or like this. And as we're talking about proteins, it can even look like this. This is a huge mess. We don't like this mess. And I'd like to tell you now how we actually determine, how we use this relatively simple law to figure out this mess here. But we are mathematicians. We can't use a law without proving it. What if we're delusional and the law doesn't make sense? So let's prove it. There are multiple ways of proving it. The simplest one would be geometrically, where you can just use the phase of the angle to figure out the new amplitude and then you will interact, but that's too easy. Or we can use Schrodinger's equation to figure out the wavelength, the phase, and everything behind the X-ray structure. But that's too complicated, and honestly, I don't understand it fully. So I'll use linear algebra. K prime vector will be the reflected angle, the reflected ray. K vector is then the incident ray. And we know that the difference from Van Lowe's theory, we know that the difference needs to be in the plane of the crystal of which you're talking about. This means the symmetry happens. Because the angles that are incident and reflected need to be equal, a certain symmetry will form. So the coordinate spaces will have a certain symmetry. We know from basic physics that the normal phase incident vector was established to be 2 pi over lambda. Scientists proved it in their experiments. And we can use this norm because the norm of the lattice vector is also known. We can square the norm of this vector. Then we use the cosine formula to get the square of the vector of the incident ray plus the square of the vector of the reflected ray minus 2 times the product of the two norms times the cosinus of twice the angle. Because here we need the angle between the two rays, which will be once theta and once the other theta. And after we calculate this, we replace the norm of the vector, we get this beautiful formula. And we can take the square root of this and get 4 pi over lambda times sinus of theta. But in the definition of this lattice vector, the norm is this one, 4 pi times an integer over the distance between two planes. If we put these two together, we get the famous formula of Van Lowe's. An integer multiple of the wavelength of the wave is equal to 2 times the distance between the planes and sinus of theta. And we know this happens because in this experiment, when the wavelength is not doesn't have such a value, the rays do not interact with each other, so we don't get any maximum minimum. This is indeed a straightforward and high precision solution, but we're using it we can use it in plenty of contexts, from proteins, from crystallography, nanotechnology, and even though it seems easy, it has a lot of implications. So let's see how we use it in determining the protein structure. This is a mind map of the process scientists go through. We have this diffraction pattern, and we apply the Bragg's law to determine the Miller indices, HKL. The Miller indices are a convention between chemists, between crystallographic chemists. which describe the structure of the crystal. HKL corresponds to certain coordinates of a plane in a 3D space. One being corresponding to XY, one to XZ, and one to ZY. Having these indices, we can use the Fourier transformation because we have this map and this data. We apply the Fourier transformation, we get the density map. But the problem with the density map, this is technically the result. This is technically the structure of the protein, but we can't know for sure this this map because of a problem I'm going to introduce later. So we have the phase problem, and this problem implies that we need to do some probabilities in our equation. We need to use some models in order to see if the proteins that we assume is correct actually make sense, and we go into a trial cycle. We make a model, we test it on our computer, how it interacts with the X-ray we use, and if it works, we'll get a good formula, and if it doesn't, we need to start over and try another model. The Miller indices are the very start. Nothing would be possible if we didn't have Bragg's law and the way it describes the structure of the protein crystal. Because if we don't know the protein crystal, we don't know the position of the atoms, we cannot use the Fourier transformation. What Fourier transformation state is it provides us with the function that it's the sum of all probabilities. This is the probability of an atom to scatter to ray times this coefficient. This formula can also be written this way, where this is the electron density map, and doing then an inverse transformation, we get the electron density map. 1 over the potential of the map of the electrons times this sum. But in this sum, we have this term, I times theta HKL, and we don't know this. This is the phase of the wave at a certain point. And how can we prove it? How can we determine it? There is no way to determine it except for some models and some probabilities. So I have to model the actual structure. And here the probabilities and statistics play a major role. Without them, we wouldn't be able to form anything. And then we have the powerful computers that we use nowadays that are able to compute and model these very big results of the proteins, because the make of the protein is not simple, it's very complex. This being said, I hope I made you understand the structure of the protein and to see that they made you understand how we determine the structure of the protein. And even though this is a field where mathematics seems completely absent, we use very complex notions such as linear algebra, Fourier transformation, probabilities, statistics, modeling. And Bragg's implication in this is also huge because it forms the very foundation of what we know today as crystallography. And without this work in this field, it wouldn't be possible to determine such important theories for nowadays medical research and not only. So thank you for your attention, and do you have any questions?
Yeah, so that was a very good talk by Loredana. I think she's happy to receive any questions about that. So, questions?
I didn't want to be the first, but there's no one asking. So proteins are dielectrics or conductors?
They depend on the amino acid structure.
Because and also I have a question: if the rays are coming parallel and reflect parallel, how do they interact with the interference?
When they come, they are in the same phase. They do not interact when they come, but when they are reflected, some of them change phases. So that's when the interaction happens.
But if they're still parallel, how do they meet?
They are parallel, but they're very close to each other. So the waves are still interacting.
Yes, I asked that because I think in my studies it was that when we speak about interference, we speak about not the rays, but about fronts.
Mhm.
And then we have this geometry that we can compare the paths and the phase difference. So probably this approach.
Probably.
Yes. So I guess my confusion is I don't understand how we use this law to study the structure. I understand that we like send these X-rays and we see how they reflect and we see these patterns of superposition. But how do I see this and then say, oh, of course, this is the structure?
We see
Like
the
this
pattern,
process, this final
we see the pattern that we have, and this peaks correspond to certain wavelengths. And we can use that data to determine the distance between the planes. And once we know the distance between the planes, we know basically the structure of the crystal of the protein, not of the protein, but the crystal that it forms. And that crystal corresponds to certain indices that we later use in our transformation.
And this phase that you cannot find after you do the inverse transform.
Yeah.
Is this the phase between the?
It's the phase of the ray at the beginning of the wave. It's like the first phase when it interacts with the crystal. Like when it leaves the
Like
generator.
the wave arrives, it reflects.
When it leaves the source, we don't know what phase it is in. Like it can be 0, it can be pi/2, we don't know. And
More questions? Yes.
When it's came to apply the Fourier transformation, in both equations I use, in both of them, if I'm not wrong, of course, the density of this is what?
electron density map.
Yeah, are we providing such information, or is it like the whole process itself to find it?
This is the process, this is what we're trying to find out.
I believe she said there's some sort of convention. The mirror indices or some convention.
Yeah.
So among us, So you perform the diffraction to find these Miller indices. Then you use the Miller indices to perform the transform
Yes,
to then retrieve the electron density map.
exactly.
Yeah, I think it's, the previous slide, the mind map is very useful. Things articulates. Yeah, well, I actually have a question, so I was waiting for everyone. So in the proof, can you go back to it? Yes. So okay, maybe not that, but it's just a little bit to the front. Yes. So how do we know this fact on the right that the norm of G
norm?
dot?
It was calculated in this convention. G is the lattice plane on the crystal, and it was calculated to be this.
So it's more of a convention among physicists.
I think it should be the condition to get the maximum, so that these two paths, the two waves accumulate. So one accumulates say n periods and another n+1 periods, and they the maximum. That's why we have this n because it can be different. And so for one occasion, we probably have the whole series of images.
So we're looking at all of the rays and okay. And just a small question at the very end, with regards to the electron density map.
Okay.
So I think there was a photo after that. Yes. So I think you said something about the electron density map there. I'm wondering what exactly that was.
This is the electron density map that we show how the electrons spread in that area, in that volume of space. And this is basically how the protein is folded and how where every atom is with its own electrons.
So the electron density map is obtained by, or let's say guessed, by looking at the frequencies, which are obtained from the Fourier transform.
The frequencies, this one?
Yes.
Well, that's the frequency of X-ray to be reflected. I cooperate with the.
Ah, okay. You have more questions for the speaker?
I have a small question. What is the typical size of the protein, like the one object that we're studying?
It's very small. It's like, I think, 10 nanometers. It's not small. It's not like,
This fraction picture, is it some unification so we can understand more
Yes.
about maximum?
More questions? If not, then let's thank the speaker once again. Work of Loredana on this project, and she is currently drafting an article, and it will be ready soon. Do you know when it's going to be ready? Loredana?
probably after.
Yeah, probably after exam season. So it will be posted also on the website for the seminar. In 5 minutes, we'll continue with our second talk, which will be by Ali Assad. So stay with us until then.